Alright, welcome to part 2. At the end of the last one, talked about how we would have to try to construct this altitude, which would be the height of this triangle down to this base level. If this were staying on the floor, how tall would that be? Well, you'd have to measure it perpendicular to the floor, so it'd have to be this kind of like extend, well, there'd actually be floor out here, even though it's not in the triangle, and it'd be the height of point A above the floor. So that's exactly what we're going to try to look for when we do this. So I don't have enough floor, so the first thing I got to do is extend the floor. And that's okay to do. In fact, I can even extend my ruler. Watch this. Cool. Alright. Line this up with there. That's pretty good. And yeah, this is a legal move to do in, oh, not that. In constructions. I thought I had my pen on there. Okay. Oh, I got it again. Yeah. Yeah, you can do this. You can say, yeah, basically I'm extending a line. I have enough information from this line, and my ruler's, that my ruler can be used to extend it. Okay, great. Then we're doing the perpendicular from a point to a line business again. But here's the point and here's the line. We just have to do the same thing. It's really the same as the last one. It's just there's this trick here that you have to extend the line so that there's enough room to do this. Is that going to cross twice? Now it's going to cross twice. Okay, cross once, cross twice. I find the perpendicular bisector of that segment now. Stab once at this end. Oh yeah, this isn't big enough. Whoops, I missed. I'm gonna make this bigger than half. Bigger than half. Looks like it's bigger than half. Do one. Whoa, that was a little much. Not really wrong, just a little too much. And then this one. Cross twice. Got the football. Swing the extra long ruler. Cross that thing twice. Do you guys talk to yourselves when you do constructions? Okay, so there's the perpendicular, great, but the part that I really care about, the part that is the altitude, goes from point A straight down to here. Now that is perpendicular. It goes to the line that contains the side, which is exactly what I needed. Okay, so that's the end of that. All right, page 2, perpendicular bisector theorem. This is also again kind of a big deal. I'm gonna right here, right on this page now. I'm just going to change my pen a little bit. Sorry, you had to watch that. Alright, perpendicular bisector theorem. Theorem 4.5. If a point lies on the perpendicular bisector, we just went to a lot of trouble constructing those. Those are the lines that go through at the midpoint of a segment, and they are perpendicular to this segment. So BC has a perpendicular bisector L that goes through A. If a point lies on L, if it's on the perpendicular bisector of the segment, it is equidistant from the endpoint. So the distance from A to C is equal to the distance from A to B. Those things have to be the same. We're asked in this worksheet to actually prove and see if that's true. So I'm gonna erase my markings I just made there. But that's what we're headed for. We're thinking maybe that's true. Okay. Why would this have to happen? So the given stuff, of course, goes here. I'm going to cheat because it's already written on the same page. I do that sometimes. Sue me. Okay, that's given. The last step I know has to be AB is equal to BC. I have no idea how that's true, but I know I'm going to need AB and BC, so let me go ahead and draw them in. By the way, you can draw in segments like that on any proof when you're doing that if you need to. Okay, why might they be congruent? Well, this is one of those proofs where, and I like to do these backwards, this is one of those proofs where if I'm asked to prove something in chapter 4, that's not about triangles congruent, there's a really good chance that it's actually a triangle congruent proof anyway. And this thing I'm asked to prove, especially if it's an angle or a side, is that it's going to be true because it's part of, they're going to belong to congruent triangle sort of families. There's going to be a triangle with AB in it, congruent to a triangle with BC in it, and I'm going to pull those off with CPCTC and say, well, they belong to congruent triangles. Now, so far, notice there's this huge gap here. This is all sort of what-if wish list stuff. I'm hoping that this is true. I'm hoping I can say there's a triangle with AB congruent to triangle with AC. Well, it looks like there is. I mean, if I'm talking about a triangle with AB in it, it's probably going to have to be triangle ABX. And if there's a triangle with BC in it in this proof, it's probably... Oh, I'm sorry. I did this wrong. I'm sure you all noticed that, and we're laughing at me going, what is he talking about? Okay. Sorry, AC. I drew it right. I just wrote that wrong. Triangle with AC in it. So triangle AC something. Oh, wait. Does ABX line up with ACX? Oh, good, it does. It looks like it does. I'm gonna go with this and hope that that's actually going to work out. Well, in this thing, I mean, the given part here is kind of a big deal. I'm given that it's a perpendicular bisector. Given that that's perpendicular and it's a bisector. In other words, I know BX is congruent to XC. Since that's equals, I'll just say equals here too. You could do congruent. It wouldn't be wrong. Why is bx congruent to xc? Well, didn't I say it was because I knew it was a bisector? Because it's a, this is how you write because it's a in proof language. Because it's a. See how I did that? It's because it was a bisector. It wasn't because it was perpendicular necessarily. It was because it was a bisector. And yeah, if it's because of a certain word, usually it's the definition of that word that's what you want to use to bleed the truth out of that. Okay, so I have that. I have a side in this triangle. Ooh, that might be part of side angle side or side side side. Looking at those two triangles again, since it's perpendicular, I'm going to go ahead and claim that yeah, that angle is congruent to that angle. I'm not even going to say why. I'm just gonna say perpendicular bisector is enough to claim that. I don't know. The book on some of those, the book gets cranky and says, "Oh, you have to actually list." You know what? Since the book gets cranky, I'm gonna go ahead and say that. Measure of angle AXC equals the measure of angle AXB because they're both 90, and that was the other part of that definition. It's because it's that's how you spell it, because it's a perpendicular bisector. But here I just really need the perpendicular reason. So this is actually kind of nice to see it this way, because there you see the word perpendicular, needed that. There's the word bisector, needed that. And the fact that A is on there means I can actually say this stuff. Great. So I have an angle, I have a side. This proof will all work out if I can complete one of the triangle congruence acronyms, like angle, side, angle, or side, angle, side. So let's look around, see what else we can get. If it was angle, side, angle, I would need angle, side, angle, I need the angle at C and the angle at B. I think in the end that'll be congruent, but there's no reason why. I don't know anything about the angles at C and B, really. But I do know something about this other side. I know something about the other side, AX. And it's congruent to itself. And that has a reason. This is how you spell duh, it's the same thing. You spell it that way. Okay, and then we're done. Because now I've listed side, angle, side, it's okay to go ahead and complete the picture that way. A good check is look back here and go, okay, side, angle, side. Do I see up in my proof a side and angle, side? In fact, they're in the same order in this proof. There's a side, there's an angle, there's a side. Yes, I can invoke this curse. Good. Take that to the bank. Alright, converse of the pivot. Oh, wait. Pivot? What's that stand for? Sounds like some kind of sandwich. Oh, perpendicular bisector theorem. Okay, great. Converse of the perpendicular bisector theorem. The perpendicular bisector theorem was if a point is on. Do I have enough room to draw this? If a point is on the perpendicular bisector, then why is that not straight? Then this distance to that whatever point it is the same as this distance. Well, the converse would be if that distance is the same as that distance, guess what? This thing is on the perpendicular bisector. So that the then part would be, well, then this all has to be true. It's kind of like that is implied by the fact that here's the before picture. I can draw all over my after picture. If that's true, then it applies all this. Okay. And guess what? The proof of that's about a whole lot of congruent triangles too. If it's equidistant there, this thing's congruent to itself. What's the rest of that proof actually? If it's equidistant to the ends of that, and if I drop a perpendicular, then that perpendicular, of course, is congruent to itself. It's perpendicular here. Oh, you know what? If I draw equal sides like that, I can use if at to say that's congruent to that, and I'd have angle, angle, side, or actually angle. Yeah, I have angle, angle, side. Okay, that wasn't asked to prove here. I'm sure it's in the book. It's a lovely proof. All right, distance from a point to a line. I have this back on here because I'm going to be doing some constructions. Distance from a point to a line is defined to be the length of the perpendicular segment from the point to the line. So in general, if I have a line, I have a point off the line, how do we say how far is A from L? That's what I'm talking about here. How far is A from L? Well, that's defined to be this distance. Like you could take your ruler and slap it down perpendicular. Here's a ruler. If I really wanted to, because we have to have this defined. We can't have this be ambiguous. To measure the distance from A to the line, you have to measure in a distance that's perpendicular. Here it looks like it's about, I don't know, 16 centimeters. If someone else came up and said, oh yeah, I can measure from A to L, it's like 21. Well, you're wrong. We can't have two different answers for that. We have to decide that there's one way to do that, and the way to do that is to really make sure it's perpendicular. Alright, I don't know if that's news for everybody. It probably is not. One of the constructions that has to do with that is, or the construction that has to do with that that's part of a theorem is as follows. Construct an angle bisector. Okay, this is a lot in one in one construction, and it's kind of small. I hope it works out. Construct the angle bisector. So I just kind of pick a radius here, and oh, okay, it's in black. I guess I like to have my answers in red. That's just me. All right, and then I construct angle bisector. We've done this before. It's been a while. I stab at where I just crossed that line. I make an arc out in space. I do the same thing from the other point I just made a while ago. There we go. There's my target for angle bisector. Of course, angle bisector has to go through the vertex of the angle. So it's something like this. Will that hit both if I just wiggle that? Oh, that's awful darn close. See, I'm running out of patience with this thing. Right. The few things I don't like about this software. The ruler just is too low res in terms of where it will snap. Okay, construct the angle bisector. Done. Draw point A on the bisector. Okay. Put it here because I think I know it's coming. If I would have put it there, it would have been a really hard construction. So we'll call that A. That was an easy step. Construct the perpendicular to each ray of the given line. Oh my gosh. Okay, so I have to make the perpendicular here, and I make the perpendicular here. I gotta do both those. That's gonna take a long time. I don't want to run time of this video, so I'll do the construction, and I'll see you in a split second. Okay, bam, they're done. I did them in different colors. You can see which one's which. The one down here is in blue, of course. The one over there is in green. Use a ruler to measure the distance of the perpendicular bisector from each ray. Okay, so we're trying to measure this. If you had an point A on the perpendicular bisector, guess what? Well, the distance from A to this line down here is about 20, a little over 20, and the distance from A to the line over there is, guess what, a little over 20. Surprised by that? Okay, so there's a theorem back on here that says if you have a point on the angle bisector, which we just made, and you measure to this line, we know how to do that, it has to be perpendicular, and you measure to this line, or you know there's a perpendicular segment there, and that's the actual distance. You know those have to be the same if this is really the angle bisector. Great, and the converse of the converse of the angle bisector distance theorem is if these perpendicular distances are the same, that, my friend, is a perpendicular bisector. Okay, I don't want this video to go past 30 minutes. If I were to do all the rest of the activities, it would obviously go past 30 minutes. So I'm going to wrap it up. Given the triangle, and I'll just sort of talk you through these quickly. Given the triangle, construct the bisector of angle A, the altitude from A, and the median from A. Well, the angle bisector of A would be the one where you go swoop, and then out in space, stabbing here, you'd go and you get an angle bisector. That thing would bisect this angle. Draw the altitude from A. That's the one where you'd stab here and cross the line down here twice, and then do the football construction on that guy. Oh yeah, pen is not fast enough to follow that. Okay, connect these dots, and actually that would go up through A. That would be perpendicular. And the median from A. Well, then I'd have to stab here and here, do a great big football. This probably wouldn't even fit on the page. Great big football from those two places, just to find the midpoint and connect that to A. So those would have all been different. Whoa, not a straight line at all. So look at how much junk is on here. It would look slightly better if it was actually done with a compass and straight edge, but not a whole lot. Same thing here. The only thing different is, no, it's all the same. Great. 3 altitudes of this triangle. Well, here's a hint. This is easier than it looks. Where's the altitude from point A to line BC? That's probably the easiest one to do first because it's going to look most like what we've already done. You do the swoop here, and then you find the angle bisector, or sorry, the perpendicular bisector will go through A. But when you do perpendicular from C to line AB, guess where that's going to go? Well, like, what's the height of C? Where is the height of C dropped down to line AB? Well, it's actually this side in the right triangle. And from B to the floor of AC, if you kind of spin your head a bit, is going to go that way. Yes, every triangle has 3 altitudes. I'm down to a minute. Perpendicular bisectors of the 3 sides. Do the football on 3 sides. What may happen is the place where those 3 intersect may or may not land inside or outside the triangle. This one's kind of a bonus. I didn't even get to this one in my other video with all the sorry, number 5. In my other video, nor did I get to number 6. 6 has all the stuff listed in the book. I am going to, no, I'm not going to do it. If I don't explain through it, it's not going to make any sense. If I get, let's make a goal. 5 emails asking me to do number 6, I'll show you number 6. How about that? In the meantime, good luck on the upcoming quizzes and tests, and have a happy November.